Task 7 is a CSG geometry-based tally, where we do tallies on both cells and surfaces, and we obtain the neutron and photon spectra. So, once a neutron is created at the source, it will go into the material and undergo a variety of reactions. We can see there's a few neutron scattering reactions in there as well. This is where the neutron changes both energy and direction. So here's one here. There's no particles, no secondary particles produced, and here's another one here. In addition to this, we may see gamma production within the material. So here's a gamma production right here. This is done by a neutron capture event, but you might get gamma production from inelastic scattering as well. So, two types of scattering. The first, simplest, is elastic scattering. This is when we have a billiard ball style collision with the nucleus, and the neutron scatters off the nucleus, normally losing energy, and that energy is given to the recoil nucleus. Both the angle and energy can be calculated simply. The second is inelastic. So, in the inelastic scattering, a neutron is briefly captured by the nucleus, and the nucleus then instantaneously readmits the neutron with less energy. It leaves the nucleus in a slightly excited state, and the nucleus can then relax the ground state by emitting a gamma ray. So inelastic scattering produces quite a lot of gamma rays. The angle of the neutron after the collision, after the scattering interaction, does depend on the energy. So here we see from this graph, at low energies, the angle distribution is fairly isotropic. So neutrons go our way in all directions evenly. However, as we increase the energy, we can see that neutrons tend to be forward peaked, and that means they're going to tend to go roughly in the same direction that they were travelling in the first place before the scattering. If the energy of the neutron does match up with a resonance energy in that nucleus, then we may see a dramatic swing from forwards to backwards scattering. So there are a few equations that are useful when thinking about scattering. The first and the most fundamental is the average logarithmic energy decrement. As we saw from the last slide, different scatters could lose different amounts of energy, so that's why we've got this average term in here. So the nice thing about making it a logarithmic energy decrement or energy loss is that it doesn't relate, the equation doesn't involve the energy of the neutron. It only relates to the atomic mass of the nucleus. So here we see hydrogen has an energy decrement of 1. It's a very small A value, while uranium, with a large A value, has got a very small energy decrement. So this equation will be used later. For here, for example, in this other equation, now we're working out the number of collisions required on average again to thermalize a neutron, or to travel from E0, which maybe we could have this as a birth energy of 14 MeV, to the final energy you're interested in, which could be the thermal energy of the neutron. This thermal energy we'll see in the example, but this is a particular energy where it's reached a thermal equilibrium with the material it's travelling through, and it could either at that point gain or lose energy. So going from 14 MeV to thermal neutron energy can be found out with this simple equation. So with hydrogen you just need 1 collision, but with uranium you need 2,000 collisions. That's an average again. So there's some other things that we should take into account. Apart from just the number of collisions, some materials have got higher scattering cross-sections or higher number densities, so they're more likely to scatter and slow down a neutron. So this is what moderating power tries to do. Here we've got the macroscopic scattering cross-section equal to the number density times a microscopic scattering cross-section. So If either of these two numbers are bigger, our macroscopic cross-section is also bigger, which makes sense. More nuclei or larger scattering probabilities, and then we get our moderating power, which is simply the average logarithmic energy loss multiplied by the macroscopic cross-section. So this is a new measurement of how good things are at moderating, and we can see that water is pretty good, heavy water is also good, carbon is not so good, and polythene is the best. The moderating ratio is something that people also want to look at. This becomes important when you're looking at efficiently slowing down the neutrons, but without capturing them. So very important for fission reactors, where they have to keep the number of neutrons very precisely known, and they can't afford to lose any. So this is the microscopic scattering cross-section over the microscopic absorption cross-section, multiplied by the average logarithmic energy loss. And you get these different moderating ratios for different materials. So the task itself looks at, after the neutrons have been scattered, recording the neutron energy spectra. So this graph here is showing neutrons predominantly at 14 MeV. So this could be at the very front of the first wall where the neutrons haven't undergone much scattering. This has got two graphs on it, and the scale of this graph is not very good. We've got a linear graph. So I'll show you how to fix that in a minute. But the second line, the green line, is perhaps showing neutrons at the back of the blanket where we don't have many neutrons, and certainly not many 14 MeV neutrons. This is showing the photon spectra. So you might notice that the noise and the energy bins are a little bit more noisy here. And this is because we simply don't have as many photons as we do have neutrons. These photons were produced via secondary interactions, so there's not as many as the original neutrons. Right, let's take a quick look at the tasks themselves now. So I'm going to run the notebook, and here I have the notebook open, and I'm opening task 7, and I'm going to do this task. I'm just going to run it all because I want to show you a graph at the end. This is the graph I wanted to show you, and if I switch to log axis, and the nice thing about this is you can also zoom in as well and cut off those noisy bins. Here we see a Gaussian distribution in the thermal energy range. So this is where neutrons have been moderated down to thermal energy, and they have a good chance of gaining energy or losing energy in their next collision. An even chance, sorry. So, hope you enjoyed the task. Thanks very much for listening. Bye.